Okay, good. Thanks. Yeah, so we have basically a 3D map of the universe from the Sloan Digital Sky Survey. So you have a lot of galaxies, redshift for each of those. So you have a biased tracer of the matter distribution. But now the question becomes, how do you interpret this map? Okay. So traditionally, we can use endpoint functions like the power spectrum, the bispectrum. But we can also do other things. For example, we can look at cosmic voids, so the most underdense regions in this 3D map. And on the upper right-hand side, I have sort of an example. So going to the right, you increase the distance from the void center. So in the center, you have the most underdense region. Then you hit this wall, and then you converge to the mean. So this is basically what a void looks like. And once you have identified these voids in your data, you can compute a bunch of different summary statistics from them. So for example, you can compute what the distribution of their sizes looks like, or what the void density profiles look like, so the correlation function with galaxies. And now the question becomes, how can we use this? How can we use these statistics? So the classic case, the most robust case, is obviously this Alcock-Paczynski type of test, which I'm not going to talk about. What I want to talk about is the aspect that voids, being these very underdense regions, are ideal to look at diffuse components in our universe. So these could, for example, be modified gravity, or dark energy, or in this case, neutrino mass. So the sort of baseline picture of neutrino mass in cosmology, you can see on the right-hand side. So whereas the cold dark matter clusters on very small scales and forms all these halos and so on, the neutrino distribution is much more diffuse. So on large scales, you trace the dark matter distribution, but on small scales, the free streaming is going to wash everything out. And you can also see this in this matter power spectrum. So this idea that voids would be interesting for neutrinos was noticed before. So here I have some examples. And basically what these find is they are promising forecasts to constrain neutrino mass from voids. But what these do is to simplify how the tracers that we use to find the voids connect to the dark matter field. Okay, so we can't do this in real data. So the idea of this project was to take this idea and incorporate all the complications that you have to worry about and apply it to real data. Okay, so this is the outline. We want to combine the power spectrum, our usual friend, with a void size function and void galaxy cross power spectrum and constrain neutrino mass. And when you think about doing this, you have the problem that you can't write down a model that describes all three jointly, okay? So maybe you have a model for each of them individually, but it's going to depend on some nuisance parameters that describe galaxy evolution. And these nuisance parameters don't map between the different models. So we apply a simulation-based inference. So we ran a bunch of simulations, which are gravity only, then put galaxies in with an HOD. And then we also noticed that the likelihood function for these statistics jointly is unknown. So we have to apply implicit likelihood inference, which in this case is neural-Ricci estimation. So these are the simulations. These are just fast PM simulations in a Planck-inspired prior. And then taking these gravity-only simulations, which don't have observable galaxies, we identify the halos, put galaxies into the halos using an HOD, and then take these galaxies, put them on a light cone, and sort of get as close as possible to the real data. So this is what the data vector looks like, the raw data vector. The crosses are the measurements. So from left to right, you have the void size function, just the histogram of void sizes. Then you have the void galaxy cross power spectrum, and then the usual galaxy auto power spectrum. And the different lines are just best fit simulations from the entire set that I ran, and looking at different parts of the data vector individually. So what you can see here is that our simulations, at least sort of at this baseline level, reproduce the data pretty well. Okay, so this is our main posterior. So I should explain what's plotted here. On the x-axis, you have neutrino mass sum. And on the y-axis, you have integrated posterior. Okay, so this is not the usual probability mass, but the integrated probability mass. And if you are along the dashed gray line, you just have the prior, so you don't learn anything from your data. And as you move into the upper left corner, your upper bound on neutrino mass becomes stronger. So what you see here is that the sort of greenish line is from the galaxy autopower spectrum alone. And then when we add the information from the void statistics, we get the red line. So you see that with this scale cut of 0.15, 8 inverse megaparsec, the voids improve the constraint on neutrino mass. Interestingly, the situation is a bit different when we include somewhat smaller scales and go to K-max of 0.2. And we did a whole investigation of what's going on there. And I think really the message here is that these one-sided posteriors, which are bounded by the prior at 0, because neutrino mass can be negative, they behave a bit differently from your usual sort of two-sided Gaussians. And with this, I conclude, and I'm happy to take your questions. Thank you.